break, and it is Katherine Kleer from Caltech, and she's going to talk to us about exploring the solar system's subsurfaces and deep atmospheres.
I'm all right, thank you. All right, great. Well, I'm excited to kick off the science talks for this meeting with some solar system science. So the intention of this talk is to give a overview of some of the most compelling science cases within the kind of planetary science realm for the ngVLA and the SKA. There are so many interesting science cases that people have written up in chapters and white papers on the planetary science side, and I wish I could cover a higher fraction of it than I can, but I will have to refer you to other talks and posters at this meeting for topics like the sun and technosignatures, but I'll focus on 5 specific science cases that I think are very compelling within solar system science and a bit of exoplanet science. And then after the break, Brian Butler will be covering a number of the solar system topics that I'm not able to cover here. So between these, you should get a pretty good broad view of what we can do with these telescopes within the solar system. So the first 2 topics that I'll be focusing on are giant planets specifically. First, talking about giant planet magnetic fields. This figure just gives a nice overview of the magnetic fields of many of the planets in our solar system to make the point that this kind of classic dipolar magnetic field that we think of for the Earth is really not universal. When we look across the solar system, we see some pretty crazy magnetic fields, and essentially we don't really understand how these sorts of magnetic fields form. Magnetic fields are generated by the interior of the planet, and so by learning about these fields, we learn something about the interiors, but especially the fields of Uranus and Neptune, which have been the least well studied, are just very poorly understood. The study of magnetic fields has really been a central focus of the community in recent years because of the Juno mission. So what I'm showing here is a model that is fit to Juno observations, that is a new model, very recent, for the magnetic field of Jupiter, and just shows some bizarre and unexpected features. And again, just shows how interesting and poorly understood the generation of magnetic fields is. So synchrotron emission from Jupiter's magnetic field dominates its emission at frequencies below 10 gigahertz. This arises from electrons in Jupiter's magnetic field. And the synchrotron emission is one of the most longest studied phenomena in the solar system at radio wavelengths. For decades, people have been imaging the synchrotron emission at Jupiter and have looked at how it varies with frequency, as shown on the right here. But the magnetic fields of the ice giants and elsewhere in the solar system are much more poorly understood. So although we have now studied Jupiter's synchrotron emission in some detail, and certainly the ngVLA and the SKA will be used to study Jupiter's synchrotron emission, looking at these phenomena at the other planets is a frontier of discovery. So this figure is showing again just how strange the magnetic fields of the ice giants are in particular. Not only are they the magnetic field axis very offset from the rotational axes of these planets, but they're both offset in angle and actually kind of from the center of the planet. So we don't know, because of these bizarre magnetic field geometries, whether we would even expect radiation belts around the ice giant planets that would produce synchrotron emission, but it would be a very interesting thing to look for to give us one more piece of information about the magnetospheres of these planets. And with the discovery of so many exoplanets that are essentially analogous, that are most analogous within our solar system to the ice giants, this is a pretty important field of study. So at lower frequencies, we also see these bursts of very bright emission from Jupiter that is probably due to cyclotron emission from much lower energy electrons than those that are producing the synchrotron emission. I stole this graphic from the LOFAR website. So these are bursts of emission that are coming from the high latitude magnetic field lines of Jupiter. And this emission is at lower frequencies than we're talking about for the observatories that we're talking about during this week. But if you increase the magnetic field strength, so if you look at the two x-axes on this plot, you can see as you increase the magnetic field strength, you increase the frequency where you see this emission. And so there has been a lot of effort in recent years to try to look for an equivalent of the diagram I was just showing you for Jupiter on exoplanets. And if you postulate an exoplanet that has a much stronger magnetic field than Jupiter's, which is like 4 Gauss, so just off the low magnetic field strength end of this plot. If you go to higher magnetic field strengths on exoplanets, then you get into the frequency range, at least the bottom of the frequency range for both the SKA and the ngVLA. So this plot is showing just upper limits. It's a nice compilation of upper limits for planetary magnetic field strengths because there is no yet undisputed detection of one of these. There's a lot of recent work. I cite one paper here that just came out a couple of weeks ago, some kind of candidate detections, but no indisputable detection of an exoplanet magnetic field yet. This would be a very important discovery, both in terms of just characterizing exoplanets in general, but also because magnetic fields are thought to be a central factor in the habitability of a planet. They protect the atmosphere from being stripped off, and they also protect the surface from high energy radiation that could make it hard to form complex molecules and life. Okay, so staying in the theme of giant planets, I now want to talk about their compositions and specifically the compositions of their deep atmospheres and how we can use that to look at volatile inventories in the solar system. This plot is showing the ratio of the abundances of different elements to hydrogen in the atmospheres of the 4 giant planets. And so you can see that because almost all of the numbers are greater than 1, all of the planets in the solar system are enhanced in heavy elements compared to hydrogen relative to the sun. And the degree of that enhancement increases as you increase in distance from the sun. So this kind of can make sense if you imagine farther out in the solar system, or if you visualize farther out in the solar system in the disk, the temperatures are cooler, you can freeze out ice particles of the primary molecules that are holding these elements, methane, ammonia, hydrogen sulfide, and water. And once these have frozen out into ice grains, they're less susceptible to solar wind pressure, and so you can get them enhanced compared to hydrogen. This phenomenon should produce similar enhancements in all of the heavy elements, or at least the sort of carbon, nitrogen, oxygen, sulfur, phosphorus, which is kind of what's seen in the planets, but there are some mysteries. For example, water in Jupiter, as you see, is depleted from past measurements. And these measurements have primarily only been made for Jupiter. You can see how few data points there are here for Saturn, Uranus, and Neptune. So the next frontier is to try to push this to the farther out planets. So in order to get the actual volatile abundance in a planet, you need to look deep into the atmosphere. And I apologize for the quality of this figure. I tried to find a better figure that made the same point, but I couldn't find one. So here we are, it gets the point across. The curve that's shown is, the blue curve that's shown is a temperature curve. And essentially what happens is you have these molecules in the atmospheres of the planet that rise up from the interior because the temperature is decreasing with altitude, when they get to an altitude where they freeze out, they do so and form a cloud layer. So if you want to look at the water or oxygen abundance in the atmosphere of Jupiter, for example, you have to look underneath this cloud layer. So you need to be sensitive to the deep atmospheres of the planets, tens of bars to 100 bars. This figure from Chris Mockel's recent paper is a pretty nice synopsis of which altitudes for the case of Jupiter, we're sensitive to at different frequencies. So the frequencies on the left, although they're for Juno, are very representative of the SKA frequencies, and on the right for the ngVLA. And each of these curves is a different frequency and shows you what pressure level in the atmosphere you're primarily sensitive to at that frequency. So we get down to the tens of bars depth within the atmosphere between these two observatories. And by observing at all of these frequencies between both observatories, we can really put together vertical profiles of the abundances of different species within the atmospheres and extract the deep abundances, which are representative of the actual bulk composition of the planet. Now, the giant planet spectra across the radio range have been observed for many years. These are the disk integrated spectra of Jupiter and Neptune, for example. And even the disk integrated spectra have been used to extract abundance ratios within the atmospheres and you can see just by eye, Jupiter and Neptune have very different atmospheric compositions as evidenced by their radio spectra. Jupiter's spectrum, disk integrated spectrum, can primarily be matched with ammonia opacity, whereas for Neptune, you require a high enhancement of sulfur in particular. But with the spatial resolution that we will get at these lower frequencies from the ngVLA and the SKA, we can look at this not just in a disk integrated sense, but actually across the surface of the planet. And this is very important because there is significant spatial heterogeneity on these planets. This is a brightness temperature map of Jupiter, and the fact that there are these bright and dark regions are indicative of regions where you have upwelling versus downwelling in the atmosphere, where you're accessing different depths. And so just those disk integrated spectra and abundances are just blurring out all of this information of what's really going on in the atmosphere. This is again a figure from Chris Mockel's recent paper, and you should go see his poster if you want to hear more about Jupiter. But this is just to demonstrate that when you can spatially resolve at multiple frequencies, you can extract abundance as a function of latitude or spatial location within the atmosphere. And when you do that, you see very substantial spatial variations. So it's important that we have this spatial resolution to understand both the deep abundances of the atmospheres and also the circulation patterns. Now, most of what I've been showing here is for Jupiter because it's been the best studied. But again, the frontier is to push these sorts of analyses to the farther out planets whose circulation patterns are much more poorly understood and whose abundance ratios are not yet constrained. The final point I want to make about the giant planets is that by observing over a broad frequency range, you're also sensitive to materials in the upper atmospheres of the planets that have originated outside the planets themselves. So for example, for Neptune, you see an overabundance of certain molecules in its upper atmosphere, like CO and HCN. And this is because you have an overabundance in the upper atmosphere where you shouldn't have too much of these species. This is actually indicative of cometary infall. So you have comets kind of orbiting outward of Neptune. Material comes into its upper atmosphere and enhances the molecules there. And so to study these processes of infall, you need very broad spectral coverage and high spectral resolution to resolve the line profiles and differentiate between species in the upper stratospheric part of the atmosphere versus the deeper atmosphere. Okay, so I want to move on now to talking about solid surfaces. So we're transitioning from giant planets to essentially airless bodies with solid surfaces. I think Brian Butler will talk about some of the solid surface planets that have atmospheres. So I'm going to talk about moons and then to get into small body populations in the solar system. So first, a bit of overview about surfaces in general. For airless bodies in particular, the surfaces of planets planets, moons, asteroids, whatever, are impacted by a wide variety of processes that change both the composition, the texture, and the density of the upper tens of centimeters to meter of the surface, as kind of an overview in this figure. Just as in the case of the giant planets, where you sense different altitudes at different frequencies, when you look into solid surfaces, you also see at the higher frequencies you're looking kind of at this upper layer that is heavily processed by the environment. But when you get into the lower frequencies, you can start to see below that. So the rule of thumb is that radio wavelengths see thermal emission. So what we detect from these planets moons and asteroids in the continuum is their thermal emission. You see thermal emission from roughly 10 wavelengths down on rocky surfaces and roughly 100 wavelengths down on icy surfaces. And just to explain a little bit more where those rules of thumb come from, this plot here, it's set by the electrical skin depth or penetration depth of the surface, which is a function of the absorption coefficient. So it depends on temperature, frequency, grain density, and composition. So just an example shown here to see where those kind of rules of thumb are coming from. So with all of the radio telescopes today and that we're talking about at this meeting, as well as thermal instruments, including James Webb and those that are going to be on the Europa Clipper and JUICE missions, once those arrive at the Jupiter system, we are going to have almost comprehensive coverage from the infrared all the way to the tens of megahertz frequencies. So we will be sensitive from the very upper surface down to maybe a kilometer within these ice shells. And I think the most exciting science for solar system moons that's going to come out of that is to get the temperature profile over the upper, hopefully kilometer of these ice shells, because that temperature profile is what gives you the internal heat flow. And especially for these moons that may be habitable or that are geologically active, their heat budget is very important and is currently very poorly constrained. But by getting the TDZ, you know, how you're changing a temperature with depth, that's what gives you the heat flow from the interior and will be an important takeaway from this combination of multi-frequency observations. So again, just as in the giant planets, for the moons, their disk integrated brightness temperatures have been observed for decades. A couple of example spectra are shown here for Ganymede and Callisto specifically. And we've gotten a lot of information just from their disk integrated spectra. But again, the frontier now is looking at these at high spatial resolution. So with the ngVLA and the SKA, we can get to the spatial resolutions that we have with ALMA today. So these are ALMA images of the 4 Galilean satellites. And just to show what the spatial resolution gives you, here is an ALMA image of Callisto, and here is Callisto with a Lambertian disk subtracted. So you can see spatial variations. You see that the low latitudes are hotter than the poles, which gives you information about the thermophysical properties of the surface. You also see a specific cold region on the surface that corresponds to an impact crater and is telling you about the composition of materials in that impact crater that is brought up from the subsurface over the course of the impact. So by pushing this sort of analysis to lower frequencies, we'll see deeper in the surface, and that will tell us whether the sort of properties that we're retrieving from ALMA are just superficial and due to surface modification, or whether they are actually representative of the deeper structure of the surface. Okay, so in addition to surfaces, I'll just say something about looking for gases. There are a few moons in the solar system that have confirmed plume activity. In addition to that, although I call these airless bodies, the icy moons all have sputtered atmospheres in addition. They're very tenuous, but you have these products of water that are in sputtered atmospheres. Maybe you have some sublimation supported atmospheres. And so with certain gas lines, in particular the OH just below 1.7 gigahertz, we can look for some of these gas species with high enough sensitivity observations at those frequencies that are right at that overlap region between the ngVLA and the SKA. Okay, so continuing on the theme of surfaces, I want to move on to asteroids and then trans-Neptunian objects. So to give a bit of background on, so I suppose I'll say the type of observations that we're making, these sort of thermal emission observations to get information from the subsurface and to get material properties, those are the same between the moons and asteroids, but the science case is very different. So to give a bit of background, this is showing essentially this. cartoon, but gives a pretty nice overview of the evolution of the structure of the solar system from disk phase to what we have today. So you can see where these small body populations, the asteroids and Kuiper belt objects, form during this disk phase, shuffle around and end up in these belts of material, such as the main belt of asteroids and the Kuiper belt. So the material that we have in these reservoirs are your remnant or your residuals of the planetesimals, or maybe residual fragments of planetesimals that were disrupted. Studying these small body populations are one of the links between the solar system part of these habitable universe or cradle of life themes and the more astrochemistry disk theme. We're studying, looking at the planet formation in other disks and specifically looking in detail at planet formation in the remnants of our own solar system's disk. So we're looking at, like I said, about these kind of residual pieces of the planetesimals. If you had a planetesimal that formed within the first few million years and that is tens of kilometers in diameter or more, which is a sort of moderate to small size asteroid today, it should have melted and differentiated based on the heat sources available. Once these objects differentiate, they undergo these impacts and they break up into all these different materials. So we think that out in the asteroid belt, there should be remnants of core, mantle, and crustal material. And by studying these individual objects, we can get information on these early planetesimal formation and differentiation processes. In addition, these collisions between differentiated objects should leave very heterogeneous surfaces of kind of the largest left behind fragment where you have potentially exposed core or mantle on the surface. And incidentally, the Psyche mission, which is launching next year, is specifically pursuing this question of understanding planetesimal core material. It's going to what is thought to be one of these remnant core fragments. So the ngVLA and the SKA will have the spatial resolution and the sensitivity to look at how heterogeneous the surfaces are, look for evidence of these this differentiation and collisional processes. Even with ALMA, spatially resolved thermal emission from asteroids, has only been done on 4 objects that I'm aware of, but the spatial resolution that you get is really incredible, and we're able to see that the surfaces are heterogeneous and look for variations in metal content on their surfaces. Extending this to longer wavelengths, and with the VLA today, this is just showing you the largest asteroids are resolved with the VLA, but only barely resolved. So imagine at the VLA frequencies being able to do this at the spatial resolution of ALMA, look for heterogeneity beneath that upper surface layer. So when I talk about this upper surface layer, I can give you a visible representation of what that looks like. On the right is the regolith. Regolith is just the word for like the crushed up upper surface layer. For the asteroid Bennu, it's bouldery. In contrast, if you look at the moon, its regolith layer is very powdery. And so with the multiple frequencies available from ALMA through the SKA, we can get the texture of this upper layer of the surface, but also see beneath it and determine whether these drastic differences that we see between the regoliths of different objects are actually representative of what's underneath, like finally be able to probe beneath the surface of this outer heavily processed layer. In addition, the polarization of the thermal emission of objects in general should give you the best information on the metal content of the surface. So in terms of looking for core fragments, you should expect to see a high degree of polarization. So that's a capability that would be very exciting. It also requires spatially resolving the object, because you get the highest polarization towards the outside of the object. And if you're not spatially resolved, the polarization vectors cancel out. Okay, so my last topic is very brief, and it is just to mention that this sort of science that we can do in the asteroid belt is also going to be very exciting in the trans-Neptunian objects, so the Kuiper belt and other objects in the outer solar system. We still are asking very basic questions about these objects in the outer solar system. We still just want to know how big they are, what their brightnesses are, what their orbits are. We're still at the very fundamental question type level. And in order to answer questions like size and brightness, you need both the reflected sunlight and the thermal emission in order to break degeneracies in modeling them. So there has been a lot of success in surveys combining optical and infrared wavelengths to get a broad view of the brightnesses and the sizes of a range of these objects. Because at radio or at millimeter, centimeter, 10 centimeter wavelengths, you're also seeing thermal emission from these objects. You can also do this sort of study, getting the sizes and brightnesses at radio wavelengths. But I think the more exciting thing that we'll be able to do is to look at the emissivity spectra as a function of wavelengths. So a couple of examples are shown here, just from 25 microns to 1 millimeter. And you can already see that for a couple of example objects, the emissivity, the behavior of the emissivity shows some interesting trends. And to extend this to lower frequencies would give us additional information on the compositions of these surfaces, potentially the components, the different ice components, which have different electrical properties. I don't know what exactly we'll see, because this field is so much still in its infancy. The low frequency observations of trans-Neptunian objects, it just hasn't been done. We haven't had the sensitivity to be able to do it. So I think this is somewhere where there's a lot of exciting discovery space still. And then finally, with the high spatial resolution, we can also do very good astrometry of binary trans-Neptunian objects. And once you have an orbit, you also have a precise mass. So looking at binary objects as well. Okay, so I will wrap up here and just point out that a lot of the science cases that I've shown here have built upon a lot of hard work that people have done writing up science cases in book chapters and white papers for both of these observatories. And finally, that there are many other talks and posters, starting with Brian Butler's talk right after the break, on the solar system and planetary science and exoplanetary science more broadly at this meeting. So plenty of other, much more coverage of topics that I have not had the opportunity to cover here. So I will stop there and happy to take questions. Thank you.
Thanks, that was great. We do have time for a few questions. There must be some. Awesome. While we're waiting for the mic to get there, I noticed that the first case that we were showing at the magnetic fields showed a lot of upper limits, but there were no kind of predictions of models on that plot. Is that just because there is not a model prediction for these?
For how strong magnetic fields on exoplanets could be? Yeah, there's no information. So we've detected, brown dwarfs have been detected in this way, but not planets. I don't know. This is beyond my expertise to know what model predictions might be in this case.
Hi, I'm Yuri van Leeuwen from Astron in the Netherlands. I work on fast transients, so I'm no expert. So if you will entertain a non-expert question, please.
Absolutely.
So I love the science. Thanks so much for presenting that. So for example, for TNOs, or maybe some of the other sources that I didn't quite understand. So is there, you say that TNOs are detectable if they're larger than a few hundred kilometers. Are they detectable or also findable? Can you explain to me the difference between finding new sources, or really they need to be first found, a different survey needs to find them, and then you can study them more?
The radio interferometers are not the most efficient way to find new trans-Neptunian objects. It is only the largest ones that we will even be sensitive to. I mean, there are a number of large ones, dozens of large ones that we'll be sensitive to, but there are deep optical surveys that are just much more efficient and effective ways of detecting new TNOs.
Yeah, thanks.
Right over there.
Oh, So another question from a non-expert. I'm just wondering whether asteroid belts are really part of the modeling of stellar system formations and planetary formations, or whether they're an accident or a probabilistic thing, or can they be predicted at certain radii, or how does that work?
Oh, so I don't have a broad answer to that question, but specifically for our solar system, So I guess if you have a system where you have a sort of planet that has a dominant mass, and you look at regions that are where the period is integer multiples of that planet, regions where you're close to being in resonance with one of those gas planets, then you have a lot of unstable orbits in that region, and so you can't coalesce material into forming a planet, and instead you'll end up with one of these belts of material. So that is one answer for where you might look for them, one in the solar system, and it's the influence of Jupiter that keeps our asteroid belt unstable, basically.
So it depends on specific circumstances in order to get this kind of thing, which may or may not occur.
Yes, when you're within the planetary region, there's sort of specific orbits on which these populations can be in. When you're talking about the Kuiper belt, that's a different phenomenon out there beyond the giant planets.
All right, I think it's time for a break. So let's thank Katherine again.